Good morning, everybody. Thank you all for coming, especially at this early hour and especially after the late running lightning talks yesterday. If for any reason you cannot read what's on the screen, the slides are already up at the Discord server, as well as a link to the code examples. So let's get started. So first of all, I'll start with a disclaimer. Accelerated standard C++ is not some kind of magic bullet. It's a really, really powerful tool, but if you think you have your legacy code and just sprinkle in one or two lines here and there, and it's going to be lightning fast, well, it might happen, but it might be a slippery slope to think that it always works. So, an outline for our talk. I'll just give an introduction and some GPU basics, so we're all on the same page. Then I'll present a sample task that I will use throughout most of the talk to explain what I'm doing. And some or many of the things that are now possible, the more or less seamless integration, is just possible because of progress made in memory access patterns for the GPU or in hiding memory access patterns for the GPU. And so I'll need to explain this. Then we'll get to the parallel C++ algorithms from the standard library. Again, something about memory, how the different kinds of, or the different ways of accessing memory will influence the use of the algorithms, the list of supported algorithms, and the limitations and pitfalls that come with using them. So a few words about myself. I'm Elmar. I work at Forschungszentrum Jülich, which is Europe's biggest interdisciplinary research center. And I work at a group named PGI, JC, and STA, Scientific and IT Systems. How we got to that name would be a story for another day. But just wanted to let you know that the PGI in the name is not related to the compiler company. Why should you trust me on what I'm about to tell? Short answer is, well, don't. Just see it as something that might be worth to try on your own. But yeah, I'm not trying to sell you anything. As I said, I'm not affiliated with any of the companies mentioned in the talk. I have about 1,000 binary years of experience with scientific GPU codes from different domains and at different scales, from your laptop or desktop GPU to supercomputers running thousands of GPUs. So, will what I am about to present work on your hardware? If you've got an NVIDIA-based system that's fairly recent, I'm positive that it will. I usually work with NVIDIA-based systems because that's what we have around. But many of the things I'm about to tell will also apply to some extent to AMD GPUs. But my experience with them is limited. So, it does not work on Apple GPUs. They do not provide a proper ecosystem to make this work. Also, they're very, very different in the technology. And their compiler support for many things is still behind. Most of the things I'm about to show you can try on your Apple, at least on the CPU, but only with a third-party library. I've seen PSTLD by Mike Kazakov. It works for the stuff I tried, and it can be surprisingly fast. So, talking about fast, you will not see any benchmarks in this talk. And that's because, well, your mileage may vary hugely. A little bit more details. It all depends on your GPU. I've seen a spread of 50x or more going from desktop to supercomputer GPUs. And also it depends on what CPU you compare against. And if you do a single-threaded versus a multi-threaded versus a GPU setup, I've seen people claiming, hey, I've got 1,000-fold speed up porting this code to GPU. And I said, okay, that's fine, but probably you should have taken care of the CPU code first. And it also depends on the actual problem you're trying to solve. Not all algorithms speed up in the same way, and it also depends on how much of your code you can actually transfer to the GPU, because, well, we'll get to that later, why it is important to have most of your code running on the GPU. And also the problem size that you're trying to solve is a huge factor. Underutilized GPU is usually well, not so fast as you would want it to be. So a little bit about the basics. A GPU system usually consists of a host, which is the CPU side of the setup, containing the CPU and its memory that we call the host memory throughout the talk, and the device, which is the GPU itself, which has a usually disjoint device memory. And the two of them are connected by a bus of a given speed. In your desktop PC, you probably have some version of a PCI Express bus. In a supercomputing world, you can have, for instance, NVLink, which is much faster, but still slower than the in-memory or the intra-GPU communication. Also, host and device usually have incompatible machine codes. So why are GPUs fast? They perform the task on thousands of threads, literally, in parallel, but the thread system has its limitations. During the execution, all threads are bundled in blocks, and the block size, it depends on the user settings or the compile time settings or runtime settings, but it's usually in the order of a couple of hundred. There is limited synchronization within each of these blocks, and also limited communication using shared memory. And the order of execution for these blocks is undefined. There's a block scheduler, and whenever one of these blocks meets the requirements for being run, it is being run, then it may be paused again, and another block is running, and so on. And there's no explicit data exchange or synchronization between these blocks. A certain number of threads within these blocks operates in lockstep. That's a system called a warp or a wavefront, depending on the manufacturer. And currently, it's either 32 or 64 threads. And this is good for synchronization, but and there is direct data exchange between threads within a warp or wavefront, but that's not what this talk is about. The other factor why GPU systems are fast is the memory. The on-device memory is usually a lot faster than the memory you have connected to your CPU, but exchanging data between these two domains is usually slow because it goes over the bus. The caches on the device are usually small compared to CPU caches, and also there are more concurrent threads that try to use the memory bandwidth. You can mitigate this by adhering to certain access patterns. The one that comes to mind is call-last access, so neighboring threads read or write neighboring data. The sample task I've chosen for today is not SexPay, as most people do, but we have this template that gets a vector and fills it with one period of sine wave. Also, for all the codes that I'm about to present, you should not work like this in a production environment. You should check the return values, you should check if you actually got a pointer, etc., etc. all the functions from the from the management libraries usually give back an error code or a status code about what happened. Read it. So the result of the sample task should look something like this, different resolution depending on the size of the vector. We have to know a little bit about the past and why it sometimes seems complicated to program a GPU. We have the classic models. They're either kernel-based and or language extensions like CUDA or HIP, which are very similar, and OpenCL, which is similar but different. Then we have a pragma-based process like OpenMP and OpenACC, and library-based implementations like Circle and Cogos. There probably are many other ways to do this, but I'll not go any further here. I'll just give you a few examples about this. So CUDA and HIP follow the same principle, and they're a superset of a subset of C++. What I mean by this is you lose some functionality coming from C++, and they add some operators or other things to the C++ standard. You can usually read the code, and with very little bit of practice, you can also write it. And what they have in common is they use a thing named a kernel, which is a small function, or can also be a bigger function, that is transferred to the GPU and executed there. And during your program run, you can do this using a special notation. We'll get to that later. But doing all of this requires a little bit of work, a little bit of knowledge how GPUs work. Both ecosystems have an API for memory and hardware management and provide some libraries for everyday tasks like FFTs, etc., and development and debugging functions, code, applications. So within these examples, or for these extensions, kernels are labeled global functions. And stuff that should be called from the kernels needs to be labeled as a device function. There are also some specialized variables thrown in at runtime that you can use to, for instance, calculate the threads that you're currently running. And if you want functions to be available from the host and the device, you need to label them host and device. Oh yeah, host is the one missing, as opposed to device. So some compiler options also allow to run const expr functions directly on host and device, which usually works, but can also fail, often silently, and this is going to be very hard to debug. As to the difference between CUDA and HIP, they're mostly the same. You can, in most cases, do a search and replace for CUDA, replace CUDA by HIP, and get a more or less running code out of that. So I'll guide you through this little bit of code that does what our sample function does, using the classic way of CUDA kernel and explicit memory allocation and transfers. So here we have a definition of the kernel with the global decorator, and down here we have to allocate device memory that can be accessed by the GPU. It goes into an extra pointer, and since this is the result of the computation that we actually want to do, we do not have to transfer it yet. The kernel is called using the triple chevron syntax given here, and we also need, among other things that we can pass here, we need to pass the number of blocks that can be calculated from rounding up the result of the integer division. And we also need to give the blocks the block size. And then we call our kernel. Within the kernel, we can, in some magic way, calculate a linear thread ID from the up to 6-dimensional grid ID that we get back from our kernel call. And block index and thread index both can be 3-dimensional, so that's where the 6 dimensions come from. And after we've done our actual computation in the kernel, we need to synchronize its kernels run asynchronously. Then we need to copy back the data that we just calculated and do some housekeeping, free up the pointer we allocated. And so that's what was done in the days of yore. Another way to do this is pragma-based. As an example, I use OpenMP here, which mostly does loop parallelizing and looks more like C than it does like C++. It's been around in parallel computing for ages and uses pragmas. There are some additional keywords now that let us run the code on GPU. The important ones here are target, map, teams, and distribute. Target is the GPU. A map is that we need to transfer memory, and teams and distribute are used for actually putting the work on the GPU. And internally, the parallel regions are compiled into kernels. And the whole thing will look like this. We just have our pragma accelerated loop here that does what our for each loop from the original code does. So there are many more ways to do it. I'll not bore you with more details about the old ways. If you want to see a terrific job of this, you can go to David Olsen's talk from 6 years ago. And the talk is actually the examples he uses are that now is that AMD uses them for their introduction into standard parallel algorithms on GPU on their website. And so we got where we are today because the memory access patterns or ways of accessing memory have changed. And only this gives us the seamless integration that we have. And yeah, back in the days of yore that I already showed you, there were different ways to do this. The usual way was tedious and slow with a double set of pointers and manually copying all the data between the host and the device. And this could also come with memory with a runtime overhead for the actual copy, especially if you had many small items to copy. We've already seen this example, so I'll skip over this. And then came something named pinned host memory, which originally was a way to accelerate transfers. A pinned memory is memory that is allocated as not being pageable. It just resides on the same memory page always, and it's easier to access over the bus and easier to transfer. But since it's not paged, it can get in the way, and too much of it may degrade your system performance. Around 2009, they utilized it in a different way, and it can be accessed directly by the device. So if you allocate a block of memory as pinned memory, you can just use it over the bus, which is convenient but slow, but it's a great way of, for instance, returning results of a reduction or something like this. And the code to do this would look like this. You can write your own allocator for pinned memory. This is about the most simple one that you can get. And inside you do malloc host for the memory or for the pointer that you want to return. And then you can just pass this data to the data member of your vector that was allocated using the pinned allocator to your kernel. And the kernel stays the same one as the one we've seen. No need of additional memory management here. Then we got managed memory, which in usage looks different. Came a couple of years later, and it's built on a unified address space. Before that, the host and the device each had a separate address space, and things had to be translated between them and transferred, like I said. And now you can deduct from the pointer, at least the libraries can deduct that, where this memory actually resides. And they also can copy your data on demand. In the early days, this was used by software, but then a more hardware-implemented approach came that uses actual paging for this. And this also allows to oversubscribe device memory. The memory that you have on a GPU is usually smaller than the memory you have on a device, but with paging data in and out, you can allocate an arbitrary amount. At least, well, there are limitations when it gets too slow because you always have to page in and page out, but yeah, it makes things easier. You have to explicitly allocate managed memory, and it only works for dynamic allocations on the heap. Your usual stack allocated variable will not be allocated in managed memory. And where the memory is actually allocated is often decided by the first touch rule. So if the first one to access the memory is GPU, it will be allocated in GPU memory first, and otherwise in host memory. What's also important is that there is no concurrent access. I told you kernels run asynchronous, but if you try to access managed memory currently used by a kernel from the CPU, it will segfault. The code looks very similar to the one before. Our allocator has malloc managed here instead of malloc host. And again, we can just pass the data pointer. So then, a couple of years ago, the heterogeneous memory management was introduced, which allows really seamless integration. And it also works by paging, but the operating system and the drivers will do everything for you. And you don't have to worry about the practicalities anymore. It's supported on Linux for fairly recent kernels and driver versions. And it is supposedly supported on Windows if you use the Windows subsystem for Linux. But I never tried this, and I only got this from the Google AI. I couldn't find an explicit source for this. It works with most NVIDIA hardware that came out in the last 5 or 6 years, and it currently works with AMD data center hardware of the Instinct series. So staying with our kernel example from before, we can just pass on the vector now, because even though it is on the stack memory, probably, or possibly at least, we can read it, so we do not have to make the distinction anymore, making life easier again. But even though you may not invoke the transfers yourself, they're still there, and they're still going to cost time. So now on to the parallel algorithms that were introduced in C++ 17. Many of the standard algorithms were extended they get an extra parameter called the execution policy. And as we've seen in the lightning talk yesterday, the execution policy is best described as something that is allowed for the compiler to do with the code you're trying to execute in that standard algorithm. So sequential execution policy allows exactly that, sequential execution. There are different levels of parallel execution. And what's interesting for us here is the parallel unsequenced execution that, because as we've already heard before, the actual problem is divided into blocks, and these blocks are executed in no given order. And that's why we need the par-unsec execution policy here. As a short example, if you want to put your sort algorithm on GPU, if supported for the data that you have, you just insert the std execution par-unsec as first parameter, and that's all you need to change. So there are some limitations within the par-unsec execution policy. Of course, the code that you run in there must be thread safe. You must take care of data races yourself using atomic operations, etc. You may not perform any allocations, deallocations, use only log-free atomics, use new mutexes, etc. And there are some more limitations for GPU code. You cannot have any access to external devices. Devices not as in GPU, but devices as in hard drive or something like that. You cannot throw or handle exceptions, you cannot access streams, you cannot pass function pointers between a host and device. As I told you, they usually have a different machine code. And this also includes dynamic polymorphism. So if you have code, a class using virtual functions, and pass an instant of this between the host and the device, it will access the virtual functions that are translated in the wrong machine code. There is no picking and choosing of which parallel unsequenced code you want to run on a GPU. If you use this execution policy, the compiler will do it. If it works or not, they're trying. If you want to call external libraries, they have to be compiled with support for the respective GPU architecture and memory modes. And if you have algorithms that you pass iterators to, usually only accept random access iterators here. So that's our sample code from before, and with support for C++20 and HMM memory, all we have to do is just replace or just insert this execution policy here, and it will run on the GPU. It's easy as that. If we have a system that does not support HMM and does not support C++20 yet, which seems to be the case for the AMD-based solution. At least I could not get it to compile, or I could get it to compile but not get it to run with C++20. We have to do a little bit more work as the reference to the vector that we use may come from the stack, which is not accessible by the device. We have to copy the data pointer from that and and can later access it from the lambda. And we can also use it to calculate our actual thread ID here or loop ID. Many of the standard algorithms are supported. Here's a list that I found of those that are currently unsupported. If it's not here, it's probably supported in one way or another. And yeah, well, no rotate, sorry, Sean. But yeah, most stuff is there. So the compilers that do this do some stuff also beyond the standard. NVIDIA's NVC++ compiler, which is there, which is not the same as the NVCC CUDA compiler, can actually also compile CUDA code and OpenMP code and OpenACC code, but it's not a full CUDA compiler. So if you have existing CUDA code and differentiate by your architecture, that does not work. We have in the old way. It's a single pass compiler now, as opposed to the earlier days. But what you can do is throw in CUDA commands like atomic add that work on the device, only in device code. And you also come with a whole set of library functions from outside. You can give a compiler flag that will allow the compiler to intercept malloc and new and replace it with managed memory calls if you are on a system that needs managed memory instead of HMM. And you have also some macros that are defined if when you're using standard parallel algorithms on GPU, plus a language extension named ifTarget that does what CUDA Arch used to do earlier. Like I said, my experience with AMD is not that big, but they also can replace your allocations optionally. And they have this hip std_par macro that will allow you to discern if you're currently in GPU code. Probably more, but not that I know of at the moment. In parallel and especially GPU code, there are some pitfalls. As in all parallel codes, you can have data races, concurrent parts, and also the standard library containers are not made for parallel use. We all already said that in GPU accelerated parentic sequences you cannot throw. And for instance, pushback throws or may throw, and so the compiler will just say, no, I cannot translate this because it may throw. Popback, on the other hand, does not throw, and it will just fail at runtime. Then, as already mentioned, you cannot access data concurrently from host and device, and you have to find your way around exceptions in total. Here's a little bit of demo code for this. So data races, we have the int named count, and if we increment this in a parallel region, we can do that. It will compile, it will not complain. We'll see later what happens. And we can put an atomic ref around an int, which will work, it will compile, and it will give the right result. We can use a completely atomic type here, which will of course also work. With the NVIDIA compiler, we can use the atomic add from CUDA, which will also work. This one would fail to compile because we use, or it may throw and the compiler tells you no. And this one will compile, but end up in the data race. So the possible output for code using this.
Atomic ref works on CUDA, like the underscore one.
Sorry?
Like, go back.
Go back.
Yeah, you don't need the if defined. The code is fine, it works on CUDA.
The remark was that the if define works
because
it works like CUDA, yes, but if we want to use portable code...
Is you don't need that macro. You can use atomic ref in CUDA code.
Yes, I know that. Yeah, the remark was that you can use atomic ref in CUDA code, but you may not want to do this because, at least with the parallel stuff, atomic ref is much slower than the original CUDA atomic add.
I'll talk to you afterwards.
Okay. So, the possible result that we get out of this code looks like this. We have severe data races for count and the pop back, and therefore get not the results that we would expect. Then there are performance pitfalls. All of this may work, but you may not get the speed up that you expect from it. And this can, there's a number of reasons for that. And one of them is alternating use of a certain memory region on the host and the device. So it has to be transferred over the bus between every function call. Here in this example, we sort some data and then we go through it using a loop, because then we can loop on the CPU, because then we can just use std_cout to print something, and then we reduce whatever the result was before, and then we have two additional data copies between the sort and the reduce, and this is slow. Then remember the first touch rule. Every time we insert a new vector here, we get an initialization process. So the members are all either filled with a given value or with a default value, and this happens on the CPU, usually if we don't do anything against it. And that way we have first touch on the CPU. Then we do something with this vector on the GPU, and this means that even though it was unused before, the data will be transferred. And then we do something with it, and if we do this in a loop, the vector is destroyed again, and then it is constructed again, and so on, and we have lots of data transfers that we do not need. So the solution here would be to take the vector out of the loop, and then your performance problems go away. Then there's a hardware limitation on mostly desktop GPUs, but also some data center GPUs that allow them to do double precision calculations with only at a slower rate, to have a selling point for the more expensive data center GPUs, and there can be a raw factor of 32 within this. So if your code does a lot of double precision computations, you may run into this trap on your desktop GPU. Then remember the threads within a warp running in lockstep. This can be bad if you have a divergent branching, especially nested divergent branching, and in a way that, yeah, the threads that are in the if case will run, and then after that the threads in the else case will run, and so on, and you get some kind of serialization of the if then else tree here. Similar problems occur if you have expensive code that runs only occasionally within this loop. And with this extreme example here, you have one execution of this expensive code in each warp, so it will install each and every warp, and you get a lot less performance than you would expect. Atomic operations per se are usually much slower than their non-atomic counterparts because they may serialize code. And also, you have some overhead in moving your algorithm or the data for your algorithm to the device and calling the actual algorithm code on the device. And if your data region, or if your data region is small and your algorithm is fast, you will not see much of a speed up here, or usually it will slow down because of the overhead. Also, you may get rare cases where you have data on the same memory page that gets paged in and out of the GPU. It's something that usually comes to you as a surprise. It came to me once, but yeah, it can happen, and it's really, really hard to debug something like this. You can mitigate some stuff by using functions beyond the standard. For example, you can prefetch data to the GPU using the prefetch async functions provided by the libraries, and this happens asynchronous. And if you do it at the right time and it overlaps with any other computations, then it may it will not cost you anything extra, and you'll see a tremendous speed up and at the first call or at subsequent calls. And as I said before, sometimes using the original CUDA atomics can be faster than library-provided atomic refs. And also here we see the if target directive that checks if we are actually on a CUDA device here. So the supported hardware, operating system, and so on for the different solutions from NVIDIA and AMD. Like I told you, everything in the Volta, with NVIDIA, everything in the Volta architecture or later, it supports standard parallelism on GPU. On Linux and possibly the Windows subsystem for Linux. Language standards are C++17, 20, and a limited set of 23. All memory models are supported by all GPUs, given the right drivers. And their compiler, it's their HPC compiler named cplusplus, which is derived from the former PGI compiler. With AMD, there is support for some of their mid to upper range consumer cards and the data center cards from the Instinct series. It works on Linux and Windows subsystem for Linux. C++17 is supported. C++20 is supposedly supported according to the documentation on ROCm version 7. ROCm is their ecosystem for running calculations on GPUs. I could get it to compile, I could not get it to run on my hardware, but this may be related to my hardware. Managed memory is supported on all GPUs, HMM on the data center models only, and they use their own version of Clang for compilation. So, in conclusion, what we have now is a powerful tool if we want to develop new accelerated codes for GPU usage. It may get tricky if you have legacy code. You have to go through your code, see if it does anything that's not allowed in the currently supported setup. And you may also have to check if it's worth it in some places. Like I said, small problem sizes, etc. And you need the support on your operating system. And you need also support by the drivers and software packages provided by your GPU vendor. So there can be a significant work that you have to, effort that you have to put on to update your existing code base. And yeah, not all problems are created equal. And you also need some understanding of what you're actually doing here on a hardware level to find your performance pitfalls. But if you just one takeaway from this talk, writing GPU-accelerated C++ code has never been easier. Just try it. So there's some more stuff that you can view or read on this topic. The talk by Dave Olson that I already mentioned. Then Bryce Adelstan Lelbach did some nice talks at the GTC conferences in 21 and 23, introducing the compilers and more general introduction of the standard parallelism for C++. Then we have AMD's documentation for their implementation of HIP std-par, as they call it. NVIDIA's compiler guide that shows you a lot of the things that are possible if you're using their ecosystems. And as mentioned before, Mike Kazakov's library that will allow you to do parallel STL algorithms if they're not supported in your ecosystem. Yeah, as I already told you before, the slides can be found on the Discord channel, and the code examples can be found in Godbolt. And yeah, thank you for your time. Any questions? And also, if you have questions, please come up to the mic in front of the podium so they get recorded for the videos.
Hi, great talk.
Thanks.
Yeah, I wanted to, sorry, I interrupted you in the middle. I was just excited.
That's fine.
Yeah, no, I'm really excited that you tried out our standard parallelism implementation and that you were able to get some work done with it. So I'm pleased. I just wanted to talk about a few points that I noticed in your slides. So you mentioned that you needed to use par unseek as your execution policy. So as of Volta and post-Volta, the threads on a GPU have parallel forward progress. They offer the parallel forward progress guarantee. And so actually par is, you're allowed to use par. There's nothing wrong with using par unseek, but you can use par.
Okay, good to know.
Yeah, and that relates to, actually on slide 10 you mentioned that the threads execute in lockstep. Actually on Volta and post-Volta architectures, they don't. Each thread has its own program counter. And so they can diverge, like different threads can go different directions. They're not required to execute in lockstep.
Within the same warp?
Yes.
Okay.
And there are synchronization instructions, but you kind of have to keep, we had people who were porting from Pascal to Volta had to keep that in mind.
Okay.
But that's one of the reasons why you're allowed to use par instead of par unseek.
Okay, good to know.
Yeah.
But yeah, still we have to, yeah, the talk had to also have the common denominator for all the solutions that are provided by different vendors, but it's good to know that's relaxed on the current hardware.
Awesome. And one more point, you talked about a STUD atomic ref. If you're having performance issues with STUD atomic ref, it might be because it assumes like a global device-wide scope, I think. So you could use from our libq++, you can use CUDA atomic ref, and that has a scope parameter that you can use to keep the atomic operations on device or even keep them within a thread block, and that should allow you to tune performance a little better.
Okay.
Yeah.
Thanks.
Thank you.
Thank you. Yeah. Thank you for the great talk. My question is, now that with standard parallelism in GPU, like automatically, do you have a mechanism or some kind of way to systematically detect when your program, let's say, is touching memory from the GPU device or from the host, from the CPU, alternatively, and then degrading performance a lot? Because it has to page, right, still.
It still has to page, yes. There are profiling tools that can give you a really fine-grained access to this data.
So that's what you rely on, right? Because before we just devise memory, you will have a segmentation fault and you find out that you were accessing it inadvertently from the CPU, for example. But now it's all automatic, right? So yeah, okay. Thank you.
Hello, thank you for the great talk. I have, I think, fairly new question. So one thing that you showed there is a host memory and device memory, and I tinkered a bit with writing some GPU code. So basically, my understanding, when you do read writes, it can be a bottleneck, and that's from device memory, not even the host memory. If this question makes sense to you. Okay.
Can you rephrase?
Okay, you make matrix multiplication or something like that on GPU, and you have you basically, when you write a kernel, you can read the bytes that you get, and you have to write them back. And in the step, you can use shared memory. So shared memory, you can use, it's cheap, but basically read writes are expensive there, and that's for device memory.
Shared memory is within the thread block, and it's usually very fast.
Yeah, exactly. Yeah.
And then there is a bottleneck going to the device memory from the thread block.
Yeah.
Yes.
Okay. Yeah. Okay.
And then there's another bottleneck going from the device memory to the host if you have to copy data back.
Okay. Yeah. Okay. Yeah. That was my question. Yeah. Thank you. And second thing, you talked about NVIDIA GPUs, AMD GPUs. Have you explored any TPU or AWS Trainium or something like that? So it's when goes out of the purpose that you're using GPUs for.
No, I have not tried that.
Okay, fair enough. Thank you.
Hello again. I have a second question. So everything that you show, more or less, I think can be implemented using CUDA trusts, even with more fine control, even if you wanted, and also more portable because you can compile with GCC and normal CLang. Is this something that your laboratory gave up doing, or?
Well, actually, what the standard library stuff is implemented using CUDA trust or HIP trust for the AMD implementation.
Okay. Mm-hmm.
So it is the front end that you can use if you want to stay with really standard code that's portable over most systems that there are.
Okay, I see. So basically you want to hide the use of trust in some sense, but at the end...
the title of the talk was Back to the Standards.
Yes,
so,
okay, yeah, fair enough. Very, very good title. Yeah, thank you.
I'm back, harmlessly though. So I noticed that your functions are taking vector by reference, non-const reference. And so if you capture that by reference, you have a reference to the host stack. And that may or may not work, depending on the support for unified memory, but it might be, perhaps, I might suggest a different practice, which is to have your function take a span of non-const. And the reason I suggest that is because you talked about, vectors have pushback and you can't call that on in a parallel kernel, it doesn't work, or it's not thread safe. And span has the correct interface, the interface that you want, which is read and write access to the elements. And it doesn't have the things that are not safe, which is pushback. So if you use span, pass it by value, if you use a span, then users, the compiler will tell you if you try to call pushback, it won't work. And so it might be a help to users to suggest to them the interface that they're allowed to use in parallel code.
Okay, using span is a good advice. Thank you. Mm-hmm. And taking a reference to the vector was done here on purpose to show that it works in some setups and doesn't work in other setups.
Right, true. Yeah, sorry, I missed that point. Okay, yeah, thank you.
Sorry, in what context it works and doesn't work? It depends on hardware or in the version of the drivers? Runtime?
Taking the reference works if you have an HMM-capable setup, because there it always works because it can also access the stack memory. And if you have a managed memory setup, it may or may not work depending on where this vector actually resides.
Okay. I have a different recommendation using span, and I think it's very sane to use iterators because they have very clear semantics. Of course, you need to pass the size and things like this, but for passing to a GPU, iterators are very nice, and it's a good alternative to pointers too, and references in this case. Thank you.
Yeah.
Thank you for the talk. Maybe a very advanced question. If I have multiple GPUs in my system, how can I distinguish between them so that I can say, please run this parallel loop there and this parallel loop there?
It's an interesting question how far the support goes within a single program. You can define beforehand which GPU you want to use using the visible devices environmental variable. And within the code, you may be able to use a select device function if you have multiple devices. I know that at least in the AMD documentation, they say this may or may not work. You're on your own here. I'm not really sure if this works for the CUDA STUDPAR implementation.
Okay, thank you very much.
I really enjoyed your talk. If I was about to try and scale up some existing C++ code base, and I didn't really know if I was going to go for CUDA or just CPU, given your opinion on the nice tools that we've got, and I just wanted to write in mostly C++, not really make a commitment to any hardware choice. So I'd be as agnostic as possible, but have both GPU and CPU scalability. What would be the best, lowest risk tool set, do you think?
It would probably look like this. If your code uses mostly the standard algorithms, then I would go to the STUDPAR implementations of the major vendors here. And the supported common denominator is currently C++17. If you need more than that, you're probably stuck with NVIDIA. So
like HPX, perhaps?
HPX, I have no experience with, sorry.
Okay, well, thank you very much.
Okay, thank you for your time. And if there are no further questions, this concludes this talk.